Namaskara. In this session, we continue our discussions on Fibonacci heap. We have to complete the analysis part of it. What we have seen is that the amortized cost of decrease key operation is order 1, although the actual cost could be lot more. That is because it has to cut a lot of ancestral nodes and move all of them to the root list. In spite of the wide variation, its amortized cost is only order 1. That is a good news because any sequence of m decrease key operations will cost order m. We will see the benefit of that, and in the meantime we will see that the delete min operation is also likewise is very expensive operation. That is because the actual cost of the delete min operation is proportional to t. Okay. Exact cost is t, where t is the number of nodes or the trees in the root list. As there is no restriction on the size or the shape of the trees, this number can be arbitrary. Okay. For example, if you keep on inserting, each node that is newly inserted is inserted in the root list as a singleton. Also, as soon as you delete the min, all its children are promoted to the root list. Therefore, the root list is going to have a large number of nodes, and the consolidation process examines every node, and whenever the nodes have the equal degree, it links and creates a tree with a higher degree. Okay. So, in the end we are going to have distinct degrees. We are going to have a root list where each root node will have distinct degree, because if there are two trees with same degree, we link them up and create a tree with 1 degree more. So, this process is and each node either stays in the root list or it is linked and then goes down as a child. Okay. Therefore, a node is either in the root list or it goes down as a child during a linking process, and once it becomes a child, it never comes up again. Therefore, the total cost is proportional to t, and by defining the unit cost appropriately, we will say that the actual cost is t. Any order t cost can be considered as t cost by defining unit cost operation appropriately. So, we see that the exact cost is t, where t is the number of nodes, and that could be arbitrary. So, delete min seem to have seem to be very expensive, right? But its amortized cost is what we are going to look at it. That is good enough, because any sequence of delete min operation is bound by the amortized cost times the number of times we perform a delete min operation. Recall that the potential of a tree is number of nodes in the tree plus 2 times the number of marked nodes. So, if m is the number of marked nodes before delete min, m remains the same, because delete min operation does not touch the marking of a node. It neither increases nor decreases. It does not address the marking at all. Only consolidation is done, link operation is performed, and the number of marked node remains the same. Therefore, if phi of t is t plus 2m, the potential, if this is the potential before let dn denote the maximum degree, right, of a root node after consolidation. Let dn denote the maximum degree of a root node after consolidation and you can have only this many trees because all degrees are distinct. Therefore, dn is the size of the root list after consolidation. That is the maximum degree. Well, dn plus 1 we can say. Dn plus 1 is the size of the root list because all roots have distinct degrees. So, there can be only one tree with the degree 0, one with the degree 1, only one with the degree 2. So, that way you may have only dn plus 1 trees after the operation. Therefore, potential after is dn plus 1 plus 2m because this is the number of nodes in the root list and number of marked node remains the same. Therefore, potential difference, which is equal to phi of t dash minus phi of t, is dn plus 1 minus t. This is the potential difference. 2m and 2m is cancelled and now you see that this is the potential difference. Therefore, amortized cost equal to actual cost plus potential difference, that is equal to d plus dn plus 1 minus t, that is equal to dn plus 1. This is the amortized cost. So, if we know what dn is, then we will know the amortized cost of delete min operation. And this is where the Fibonacci numbers come into picture, the name Fibonacci heap and everything comes into picture. Okay. So long we haven't even mentioned why this structure is called the Fibonacci heap. Right. There is no trace or any discussion related to Fibonacci numbers or anything so far in the discussion. Right. Here now you will see that Fibonacci numbers are coming into picture. Okay. So what is dn? We are going to show that dn is order log n. We are going to show this. So in order to prove this, we need a technical lemma and some properties of Fibonacci numbers. What are the Fibonacci numbers? F0 is 0, F1 is 1 and Fn is Fn minus 1 plus Fn minus 2 for n greater than or equal to 2. So 0, 1, 1, add the previous two terms and get the next one, and this is the Fibonacci number. The Fibonacci numbers have got several interesting properties. The following property: for all k greater than or equal to 0, f of k plus 2 is 1 plus sigma I going from 0 to k of f of I. So add all the term up to f of k and add 1 to it, you get f k plus 2. Okay. So this is absolutely easy to prove by induction, trivial proof by induction. Okay. And we can also prove by induction that f k plus 2 is greater than or equal to phi power k. What is this phi? This is called golden ratio, 1 plus square root of 5 by 2, which is roughly 1.62. So f k plus 2 is greater than or equal to, it is exponentially growing values. It is growing at the rate of phi, right. Therefore, f k plus 2 is, and both these proofs very easy and direct proof by induction. Both these facts can be absolutely easy to prove by induction. So this is the technical lemma that we need. Let x be any node in a Fibonacci heap after consolidation, that is after tree link and everything is done. Let x be a node in Fibonacci with degree of x equal to k. Let x be any node in Fibonacci heap after consolidation with degree of x equal to k. Let y1, y2, yk be the children, degree of x equal to k means x has k children, be the children of x ordered by the time they have become a child to x. So y1 is the among y1 to yk, currently x has got y1 to yk as children. y1 is the first to become the child. y2 is the next to become the child, I mean later than y1. y3 became a child later than these two. These are all the surviving children. Then degree of y1 equal to 0, degree of y1 equal to 0 and degree of yi is greater than or equal to I minus 2 for I 2 to k. Degree of yi is greater than or equal to I minus 2. That means x consists of children that are of high degree. Okay? Each child has got sufficient degree. Okay? Degree of yi is greater than or equal to I minus 2. We will see the consequence of this property. This shows about the density or the size of the subtree rooted at x. Okay? Size of the subtree rooted at x. This has an important implication on that. We will come to that next. First we will see this property. This is somewhat easy to let us consider the time at which yi becomes a child of x. Consider the time at which yi became a child to x. So when will this happen? Only when the degrees are equal. Linking is done when the degrees are equal. So x had the same degree as y, and yi has become a child. But when yi was introduced, when yi was considered, x already has y1, y2, yi minus 1 as their children. Probably it may have something more, right? It may have something more, and therefore the degree of x is greater than or equal to I minus 1. It may have something more which it might have lost later on. When you are considering x as y1 to yk, at the time of introducing yk, x will definitely have all of them, because these things are surviving till the end. They are there at the time and they will be there even after that. But it might have lost some children by the cut property. But at the time of yi, maybe it had something more. It does not matter. Definitely degree of x implying that degree of yi is greater than or equal to I minus 1. It is still in the tree. It is not yet cut. It might have lost one child. When you lose one child, you simply mark it. You do not cut it. It will remain as a child of. If it is losing one more child, then it will go to the root list. It will not be a child of x. Therefore, after this, after yi becoming a child of x, it might have lost at most one child. If it is losing the second child, immediately after losing one child, you are marking it. And if yi had lost one more child, yi will not be here as a child of x. It would have moved to the root list. Therefore, it might have lost at most one child, implying that degree of yi is greater than or equal to I minus 2. Degree of yi is greater than or equal to yi minus 2. The first vertex that you are adding obviously will have degree 0, because x also will have degree 0, and yi is the first child. Before that there is no child. That means degree of x is 0, and y1 has become a child means y1 also should have degree 0. Therefore, degree of y1 is 0 and degree of yi is greater than or equal to I minus 2. Okay. What is the implication of this? Let Sk denote the size of the smallest tree rooted at a node with degree k. Let Sk denote the size of the smallest tree rooted at a node with degree k. Now, your x which has a degree k is looking like that, the x, y1, y2, yk. This has got at least, as per the notation, S1 nodes, this has at least S2 nodes, this has at least this has got at least S0 nodes, this has got at least S0 nodes, I minus 2, yi. This has at least I minus 2 nodes. Okay. This has got at least k minus 2 nodes, because yk's degree is greater than or equal to k minus 2. Therefore, it will have at least sk minus 2. That means this is the size, sk is greater than or equal to 1 is for this node, y1 is S0, this is 1 plus sigma I equals 0 to I equal to this one 2 to k, well 0 to k minus 2. S0, S0 plus S2 plus Sk, Si. This one is for the root, this one is for y1, this is for x, this is for y1, the size. This is from 2 onwards, S0, S up to k minus 2. So, Sk is greater than or equal to, this is equal to 2 plus sigma I equal to 2 to k, changing the index, I minus 2, and this I can write as 1 plus I minus 2. I write like this. So, Sk is sum of all the, that means S is going to have exponential growth, right. So, we are going to now argue that Sk is greater than or equal to Fk plus 2. Sk is greater than or equal to Fk plus 2. Again, the proof is by induction. Proof is by induction. So this is greater than or equal to 1 plus sigma I equals 2 to k of S I minus 2 is greater than or equal to Fi by induction hypothesis. By induction hypothesis, this is the case. But one is F1. F0 is 0, therefore this can be written as 1 plus sigma I equal to 0 to k of Fi. This can be written like this, which is nothing but Fk plus 2. We have already seen that this is Fk plus 2. That means Sk is greater than or equal to, which implies Sk is greater than or equal to Fk plus 2. We assume this and we have proved this by induction. Therefore, this is a straightforward proof again. Therefore, you can see that Sk is greater than or equal to Fk plus 2, and this is greater than or equal to phi power k, which is roughly 1.6 power k. Therefore, what is the relation between k and Sk? It is a log. Okay. Therefore, k is less than or equal to log to the base phi of Sk. All right. So this is the degree. So what is the maximum size you can have? All nodes in a single tree, right? Therefore, size of the maximum size of a tree can be n. Therefore, the max degree can be less than or equal to log n to the base. So if k is the degree, then it has got at least Sk nodes. It can have maximum n nodes. So what can be the maximum value of k? K is less than or equal to log Sk. Maximum value of Sk is n. All nodes can be in the tree. Therefore, k is less than or equal to log n. That means the distinct degree. Now changing the base, this is order log n to the base 2. Base changing rule alters only by constant. Okay. Therefore, dn is order log n. Maximum degree is order log n. If maximum degree is order log n, this implies amortized cost delete min is order log n. Amortized cost of delete min is order log n. So Fibonacci heap has the following property. Insert order 1, both worst case and amortized cost, both of them is order 1. Delete min order log n amortized cost. Actual cost could be as much as the number of nodes in the root list, but amortized cost is order log n. Similarly, decrease key order 1 amortized cost. Actual cost can be lot more, but amortized cost is order 1. This is the key property of Fibonacci heap. So Fibonacci heap is a data structure that has got delete min and decrease key in order log n and order 1 amortized cost. This is an ingenious data structure. It is one of the very cleverly designed data structure, and its analysis is also very elegant. And finally, we could argue that the amortized cost for the operations are very interesting and impressive expressions, order log n and order 1. We are going to see the effect of, or the effect of such an improvement in our another minimum spanning tree algorithm. We are going to look at another minimum spanning tree algorithm called Prim's algorithm. Prim's algorithm for minimum spanning tree. And we will see that this particular data structure can be used to improve the asymptotic complexity of the Prim's algorithm. We are going to see the details of that in our next session. Thank you.